Okay, so now we're up into the 1900s. 1917, Hardy, English mathematician, Ramanujan, an Indian mathematician, and a lot of people regard him as being one of the most incredible mathematicians of all time. He grew up in India and just would write down these mathematical formulas and nobody could understand them, and not all of them, but a lot of them turned out to be right and groundbreaking. Yeah. And then in the 1940s, Erdos and Katz also refined the Hardy-Ramanujan theorem, and it answered the question, first question from last time. How many primes are there dividing the number x? And we're going to count them as distinct. So like 18 is 2 times 3 times 3. So for purposes of these theorems, we would say 18 has 3 divisors.
Yeah.
Okay. And they found an incredible thing. The number of primes that you would expect to divide into a number x is approximately log of x. Isn't that strange?
Yeah.
So first you sort of take the number of digits, and then you take the number of digits of the number of digits.
Whoa.
What? Pretty amazing. And even more amazing is what Erdos and Katz did to revise the Hardy-Ramanujan theorem. Hardy-Ramanujan said this is what we think the number is.
Yeah.
And then it's not always going to be true, right? So the number of primes dividing a prime is how many?
It's the number.
How many primes divide a prime?
Just one.
Just one, right?
Itself.
So, but there are super large primes, right?
Yeah.
How do we know that?
Well, there's infinite primes.
There's infinitely many, so they must get pretty large. So this isn't always going to be exactly right, and that's why it's only an approximation. But Erdos and Katz showed exactly how it's wrong, which is amazing. And what I mean by that is they show that if you have this number, if you have your number x and you make a graph and you have log x,
Yeah.
you have this what's called a probability distribution around log x. Okay? And you've seen this kind of thing before in when we're flipping coins.
Yeah.
So remember, if you flip like a coin, flip 2 coins, you can get heads, tails. Oops, sorry. Tails, heads,
And 2 tails.
2 tails. So you have 1, 2, 1. So you have a hump in the middle.
Yeah.
Then it goes 1, 3, 3, 1. 1, 4, 6, 4, 1. So you've seen this kind of hump before.
Yes.
This is also Pascal's triangle.
It's also Pascal's triangle. And so this distribution, which is called the normal distribution that Erdos and Katz found, looks like Pascal's triangle.
Yeah.
Okay, so when you get really big numbers, where log x starts to get big, 1 prime divisor is over here, and it means it's very, very low probability. It'd be like flipping 20 coins and getting all heads.
Yeah.
It can happen, right?
But it's not likely.
It's not likely to happen. So the primes, big numbers are far less likely to be prime, and Erdos and Katz showed exactly how that probability works.
Cool.
But here's the double, triple, super, infinitely amazing thing about this. Aristophanes showed how to construct all the primes, right?
Yeah.
Primes aren't random. They're not like flipping coins. They're completely determined, right?
Yeah.
Nothing's random at all about them. But yet, this math of random numbers ends up describing them. Yeah, it helps a lot. And this is one of the things that nobody understands. No one understands why primes should be described the way random numbers are described.
So they're random, but like they're not supposed to be random.
Right, they look like random numbers, but they're not random at all. And 2,500 years ago, we knew they weren't random. So this is one of the most beautiful theorems in math, this Erdos-Katz theorem, that shows exactly how primes behave. And the reason it's so beautiful is because you would never, ever expect probability to describe primes, but it works out pretty well.
Whoa.
So now we're up to 1917 and 1940. You ready to come up to today?
Yeah.
Yeah.
All right, here we go.